Thank you for the invitation. I really appreciate it. And I think actually the fact that I'm following Cody is really valuable because what I'm trying to talk about is basically the sort of thing that he was describing as a concrete example of how these sort of communities on the periphery can have a really huge and positive impact, I believe. Um, okay, so I'm assuming I'm heard, I'm seen. So yeah, so I want to start. This is Paul Erdos. I assume many of you, but perhaps not all, have heard of him. He is somewhat rare in that he's maybe one of the 5 or so most prominent mathematicians of the previous century, a bit of a celebrity. And the reason for that is partly the math that he did, partly how he did math, and just partly who he was. So amongst mathematicians, Erdos was uniquely collaborative. And I mean, there are bibliometrics to tell us that over time, mathematicians have become more collaborative. In the past, it was pretty common to write solo-authored papers. It still is, but less so. And Erdos was unusual, especially for his times, in how collaborative he was. So he wrote over 1,500 papers. Very few people have done that in any field. He had over 500 collaborators, which again in math I think is truly unique. He's so sort of central to how mathematicians communicate to each other that he is, I would say, I mean, so we measure the sort of collaboration graph of mathematicians by how close you are to Erdos. So the Erdos number is just how many steps from you to collaborator it takes to get to Erdos. And some Erdos numbers. So my own is 3. My first paper is with someone named Ben Young. He wrote a paper with someone named Bruce Richmond, who quite likely is in this picture on this slide. I looked up all the other speakers' Erdos numbers. So Alan Kay's, notice I'm putting less than or equal because it's hard to know for sure that you've found the shortest path. But Alan Kay, Nick Patterson, less than or equal to 3. Our speakers today, less than or equal to 4, I guess, except for Carter at 5. And even Peter Watts, it took a little bit of extra work. The normal calculators couldn't find it, but with some help from ChatGPT, I found it down to less than or equal to 6. Sorry, Yushi, and I couldn't find your publication list, so I couldn't get started. And Brian doesn't seem to have collaborated with anyone in the sense that this gets counted. But I think one important takeaway from this is that he's used as a central figure, not just for math, but actually for all of academia. Any academic, you can generally find a path to Erdos. And it's pretty exceptional. So if you've heard the concept 6 degrees of separation, which is very on theme with many of the talks we've heard today, you'll notice that less than or equal to 6, even for the field biologist. Okay, so there's a really charming biography of Erdos. It's called The Man Who Loved Only Numbers. And you'll learn a lot about his life. So some things you'll learn about are his upbringing. So I say The Last Martians. Maybe if anyone wants to pipe in and remind us what the Martians were or who the Martians were.
The Hungarian mathematicians, physicists, scientists.
Yeah, and specifically they were Jewish, sort of at the beginning of the 20th century. So he was amongst the last Martians in that, right, he's born in the 20th century. Many of the other prominent ones were born earlier, and I would argue the reason for that is that you had to establish yourself as a prominent enough figure to escape the Holocaust. And it is difficult for someone in their early 20s to have done so, as Erdos did. So another unusual feature is that he did not have a residence. He just traveled week to week, staying with different mathematicians in their homes. This is part of how he could be so collaborative in a pre-internet era, is that he was constantly with new mathematicians. He had a lot of unusual behaviors and habits. He didn't know how to butter bread or do laundry or pay someone to do laundry. He had a unique vocabulary. He called children epsilons. Rather than saying someone died, he said they left. When they died, that meant that they stopped doing math. And I mean, there's a reason they call him the man who loved only numbers, right? He really devoted his life purely to mathematics. Now, his mathematical accomplishments, there's a distinction in math commonly drawn between problem solvers and theory builders. And Erdos is fully on the problem solver side. And so what that means is that he didn't necessarily do many things that were individually so impactful. It's more that he had a very large bag of tricks. He encountered problems from his travels. He solved them, or he identified the people who could solve them. And he served as this bridge, right? It's not a mistake. He was at the center of this collaboration network, partly for his lifestyle, but also partly for his approach to mathematics. So you can read this book. You'll learn about a lot of these things. It's a lovely book. But you won't actually learn that much about the numbers that he loved. And so my original goal in this is to share a bit more about how he did math, what he gave to math, and I'm going to pick it through the lens of he did a great deal of work on graph theory and specifically random graphs. Now, we've seen a lot of graphs so far already this talk, because what is a graph? For those of you who don't know, it's a collection of vertices, some of which are connected by edges. So this is used to model essentially any relational information. So I wanted to give a very brief history of graph theory, very, very brief. The first appearance is arguably in Euler's solution to the bridges of Königsberg problem, which is early 18th century. And it's a very natural concept to think you have some dots, some of them are connected. So on the right, there's a graph illustrated. And so you have a very ad hoc development because it's such a natural thing. People will encounter it as a useful abstraction. They'll ask a question about it coming from a specific context. And it wasn't really until the mid-20th century that graph theory coalesced as sort of a field in its own right. So in the 19th, 20th century, you encounter a variety of natural objects. So trees were studied in the study of polymers and chemistry. The four-color theorem showed up coming from essentially a recreational problem about maps and how they can be colored in. Kirchhoff did a lot of work related to graphs via his work in physics on electrical circuits. Then in the 20th century, right, it coalesced. Now, I think that one of the reasons why mathematics sort of develops is that it can solve certain problems that people care about. And that might mean caring about them from a mathematical perspective. In this case, it really was about real-world utility. So communication, a lot of foundational graph theory work was done at Bell Labs. In fact, many of Erdős's collaborators were at Bell Labs. And Bell Labs needed this because they had telephone networks. They needed to know on a theoretical level how best to set up their switchboards, how best to connect various parts of the country. It's a very practical question, and it leads very directly to this sort of relational model. Other major examples, so in optimization, you like early rail networks, there were questions where this proved to be the right theory. And then once computer science developed, so many questions in that setting can be described via this type of relational information. And I think that's really where it truly took off. Okay, so it's a language to describe things. So we've talked about phylogenetic trees and also more complicated models with intermixture. We've talked about academic collaborations, neuron connections, organizations, which philosophers were talking to which philosophers. All of these are models best described using graphs or sort of slight variants thereof. So again, I don't think I'm saying anything new to most of you, except that I want to emphasize, right, this is a theory motivated by applications more than anything else, I would say. And so when you get your applications, right, so we describe this field in terms of objects, but really the practice is defined by the questions that it attempts to answer. And so one major one is connectivity. Which vertices are connected by paths? How can we tell that different vertices can be connected by paths? How do they group together? So again, thinking about telephones, right? Can you actually chain a call through a switchboard from New York to LA? It's not clear how to do that. It's also not clear what the best way to do that is. And so optimization, a classic question is, what's the shortest path satisfying some constraints? So this, like I mentioned, it can be railway routing. It can be the traveling salesman problem of how do I like go in a circuit between some cities along the roads available to me. It can also be about matching theory. And through that lens, it sort of becomes a question for any resource allocation problem. A lot of these were studied by economists through the lens of resource allocation. So Hall's marriage theorem, for example. Then there are extremal questions. So example, how many edges can you have in a graph with no triangles? And extremal questions are, I think, where it frequently starts deviating somewhat from these very applied contexts and becomes more of a question about graphs for graph's sakes. And I'm not saying that that doesn't happen in the above settings, it certainly does, but extremal, I feel like, is maybe the first setting where this became the standard outlook. So the no triangles question was answered by Mantel in 1907, a Dutch mathematician, but really I would say this is a Hungarian tradition, in fact. Like many of the early practitioners, even before Erdős, were Hungarians. And Erdős became enormously influential in promulgating this lens of graph theory. And then there's also structural graph theory, which he did less of, sort of how to characterize graphs satisfying some constraints or sort of features of graphs. So how could you characterize graphs that can be drawn so that none of their edges cross? I think actually a lot of the measures that we were talking about, like how do you measure? So in the previous talk, there's the question like, how do you measure centrality in a graph? And there's a lot of different metrics. And I would say that many of these metrics are sort of structural in nature. So you have this broad swath of questions you can ask. And maybe I'll say that structural questions tended to be more thoroughly investigated in the West, as opposed to extremal questions, which showed up more in the Eastern Bloc and specifically in Hungary. And there's some just, I think, historical sort of sociological developments and path dependency that led to this. And so a key point I want to say, and I think this ties into the previous talk again, and maybe to many others, is that different communities are going to ask different questions. But it was during the 20th century when they really started talking to each other. And this is what I mean when I say that it sort of coalesced into a field. Okay, does anyone have any questions about our setup so far? I'm going to wait 20 seconds. I would like a question in that time, but no pressure. Random graphs equal random matrices. Very strong connection. Some random matrices can be viewed as random graphs. So I'm not going to explore that connection in my talk, but it is very much a setting where some of the things I'll be saying apply, that there is sort of a translation where properties first identified in a random graph setting then translated to another context. So nice question, and thank you, Sam, in the chat. And maybe I'll mention too that this is sort of another example of a common theme we'll see, which is that a lot of toy models are easily described in terms of graphs. So you might have a very complicated real world situation, and you might be able to reduce it to some sort of graph data with a lot of loss. Or you might just be able to describe an analogous setting about graphs specifically, understand that, and then sort of hope that your understanding there lifts to the more complicated real world setting. And we'll see that later. Okay. And then there's another key issue I really want to identify, which is that there are too many graphs. So if you have 100 vertices, 100 nodes to connect, depending on how you count, that there are over 10 to the 1400 graphs. So a 10 followed by 1400 zeros. That's just not a number that makes sense in any physical way. And so you can't do exhaustive study of large graphs or even small graphs. I would say 100 is small. And people have just terrible intuition for how they might behave. So this is, I think, one of the fundamental problems of the field, especially when you move away from questions like connectivity and optimization, where you have this sort of like very physical understanding of the problem, and start moving more towards extremal and structural questions, is that you just don't have an intuition that is particularly helpful for understanding these types of questions. So you have to really think very hard, and you have to sort of look for slices that you can make sense of. And this is something that I think Erdos really was exceptional at. Okay, so Sam asked about random graphs. It's probably worth saying, what is a random graph? And this is not the only model. In fact, it's not the first model. We'll see that later. But I think it's the most influential model of a random graph. So you take n vertices, and you basically flip a coin for each pair. And if the coin is heads, you connect them. If the coin is tails, you don't. And then you have some probability p of getting a heads. So here's a few examples. If p is 0, you will never have an edge, right? You just can't. The probability that they connect is 0. It doesn't happen. If p is 0.1, then about 1/10 of the pairs get connected. So if you look at this example, there are 20 vertices, which means there are 190 possible connections. Is that right? No. 20 times 19 over 2, 190, yes. So there's 190 possible connections here. And that means that you would expect about 19 edges in this picture. And I don't know if I haven't actually counted, right? It's not going to be exactly necessarily. 1, 2, 3, 4, 5, 6. You can keep going. By the same reasoning, if p is 0.2, you're going to have about about 38 on average edges, and it starts looking pretty dense. And as p gets bigger, it would look denser, right? And notice that this graph on the right, there's this one isolated vertex, and otherwise everything else is sort of, you can get from one place to another along edges. Over here, there are multiple isolated vertices, and I'm trying to see if there are, yeah. Okay. So if we look at this one here, oh, I'm wrong. I thought I was going to say that it was going to be part of its own small component, right? But then we have this edge, which connects it to other things, and so they're actually all connected, the ones that have edges. Fun. Okay. All right, so why do this? Why use some model of a random graph? Why use this model? And the original answer is that this was a tool in Erdős's bag of tricks. Like I said, large graphs are incomprehensible. These graphs are relatively sensible. You can make sense of them. And so the first application was in a paper in 1947, where Erdos used it to construct a large graphs with some specific properties. Going into the details of that first paper is a little more complicated, but I can give an example concretely. So the girth of a graph is the length of the shortest cycle. So what that means, right, is that a cycle just means going in a circle, essentially. You're going from one vertex to another, then you get back to where you started. You never go anywhere more than once. So to have a large girth means that you don't have any short cycles. So a girth of 4 means you have no triangles. And it's natural to ask, okay, can I build a graph with a large girth, but also a lot of edges? And I won't try to quantify what I mean by a lot. And it's not too hard to show that there are some fundamental limits on how many edges I can have if my girth is large, but can you build a graph that looks like that? And sort of the answer is, for the right value of p, perhaps with some small modification, every graph looks like that, which I think is very unintuitive. And this is a common feature, like I said, that large graphs are incomprehensible. Having a model like this gives you some comprehensible class of graphs, and often things that seem impossible are in fact always the case with this type of class. So this is something called the probabilistic method, which Erdos introduced. It is a fundamental tool now, not just in math, but in a variety of disciplines, especially computer science, and shows up in physics. Well, all of math shows up in physics. So I don't know how meaningful that is, but make it a little more concrete later. Okay, so in the end, right, I'm saying this was introduced as a tool, a trick, essentially, to get a handle on some large graphs. Okay, continuing, it wasn't until about a little over a decade later that Erdos, together with Renyi, another Hungarian mathematician, studied random graphs sort of as their own object. And in fact, this was done independently by Gilbert in 1959, Gilbert being a Bell Labs employee. And they both studied connectivity properties as sort of the first things to look at. And the first question that they both asked is, for which P are a given pair of vertices going to be connected, or likely to be connected, perhaps is a better phrasing. What about if I want every pair to be connected? And I don't mean just by one edge, I mean in the same component. I can travel from one to the other. So this was the first question that they asked, all three of them. And then there was a second question that was not in the Gilbert paper, only in Erdos. For a given P, how many vertices are in the largest component? Right? What's the largest value where I can get from the vertices in this collection from one to the other? Does this question make sense? Or maybe, does anyone have any clarifying, want some clarification here? Okay. All right, so are these good questions? Does anyone have opinions about that? I would like at least one opinion. Are these good questions? Okay,
Yes.
Johan?
Sorry. Yeah. I was sorry, Zach. I had some audio from. I don't know why my
Oh,
audio
that's
wasn't
fine,
turning
yeah.
on. Yeah, I just kept fiddling with it. Anyway, yes, yeah.
Okay, so I think the first question is actually kind of boring. And the reason it's kind of boring, and this is where I betray that I'm a mathematician, is that it's too easy. I could give this as a homework problem, essentially. The Gilbert paper is 4 pages, and one of them is references. So it's not that this is a bad question in the sense of from a practical perspective, I think that it's probably on its face a more important question. But from a mathematical perspective, it's kind of lame. It basically just boils down to Poisson approximation, which is a standard method from the 19th century. And so it's not so exciting. Whereas the second question is outstanding. And the reason it's outstanding is because it reveals some structure that we didn't expect to be there. So what Erdos and Renyi showed is that when P is small, you get tiny components. By tiny, I mean logarithmic in n, where n is the number of vertices. When P is big, you get a giant component plus a bunch of stragglers, a bunch of tiny components. So you have one big component, which will have about a positive fraction of the vertices. And then when P is just right, it's complicated. So this is what I mean when I say that Erdos collected amazing questions. And he came up with amazing questions. This question, I don't think anyone hearing it for the first time will have the right intuition unless they've sort of seen it in another guise. It requires deep thought. It required, in this case, a community of effort to really make sense of what's going on in the just right regime. And it's still actively studied. Proved to be the first example of a very general phenomenon. So let me talk now about criticality and thresholds. So they said, okay, so what do I mean by just right? I actually mean 1 over n. So when P is less than 1 over n, going from less than 1 over n to greater than 1 over n, the largest component goes from tiny to huge. And so what do I mean by less than 1 over n? I mean like 0.99999 over n. And what do I mean by bigger than 1 over n? I mean 1.0001 over n. Just like a positive move away. Sam is likening this to domain growth and shrinking in magnetic material. Yes, that is, in fact, totally the right intuition. I will touch on that momentarily. Not literally that, but very similar. Okay, so this critical value is 1 over n, and that's what Erdos and Renyi identified. And then understanding the behavior at criticality took decades, and it's arguably ongoing. So in 1984, Bolobash, he didn't look like that back then, identified the width of the window, right? How far away from 1 over n can you get while still looking like 1 over n? The size of the largest components within that window. It turns out that they are the size of the largest component will be roughly n to the 2/3. I don't think there's a good reason to guess that value. Again, it's just not, I don't think there's a physical intuition that explains it. Or maybe that's not quite true, but it's a deep one. Also some other structural features. And then there's a ton of follow-up work, relative sizes of components. It turns out that they satisfy a power law. So they're n to the 2/3 times some constant, and those constants demonstrate a power law, like we've been hearing about. What they look like, there's a huge literature on this. And then also we get out of this a whole theory about graph thresholds, threshold phenomena on graphs. And I'm not mentioning, but there's other models. So if you've ever heard of a bipartite graph before, you can do something very similar. And you can ask all the same questions and get very similar behavior, but showing that is something that took another 30 years, 40 years after Bolobash. The stochastic block model that was previously mentioned in Cody's talk, you can ask the same sort of questions. That's an ongoing area. I would say that they're very much working on that now. These threshold type phenomena, that was an enormously valuable thing to study and has profound applications. So like, I would argue it indirectly gave us Malcolm Gladwell's tipping point, right? It's the mathematics that underpins those sorts of sudden transitions. Okay. And the takeaway I want here is that when you come up with a good question or type of question, a whole community develops around it. And in mathematics, it's good enough for us that it's hard, but tractable. It's unintuitive, but revealing. And we don't necessarily need applications. So this question and related methods, the methods that got developed to answer it, but also sort of related questions, really evolved into a large community with Erdos at the center. And I think that that's not a given that this would happen. So Bolobash was a protege of Erdos. Erdos started talking to him about math when he was 12, I believe. And many other figures in this community met Erdos at very young ages. My advisor did his PhD in a completely different area of math and then met Erdos shortly after getting his PhD and switched fields into this. So when I say a community develops around this body of work, and I say Erdos is at the center, you could say a better way of phrasing it maybe is that Erdos created a community to surround this body of work. Yeah. All right. So this is not uncommon for how I think mathematical areas, sub-areas form. But normally in order to develop this degree of maturity, you need some sort of applications, whether that's to math or other areas. And the first application of random graphs, I would say, is to percolation. So the idea is we start with an infinite grid. Obviously, I've only drawn a tiny piece of it. And each edge is kept with some probability p. And this is the same question, just a different underlying object. So you can see, I think, very directly that this should be a similar model. Now, this was studied in the 1940s by physicists first. And the questions they were asking is, what do the components look like? Which value of p is going to give us an infinite component? I mean, they're asking basically the same questions. But their motivation is very different. It's because this is a model of phase transitions. So what Sam was saying about magnets and how their domains grow and shrink, I think that's an example of a phase transition in physics. A more classical example, right, is sort of transition of materials, say from liquid to solid. Okay, so this is a similar setup. It's a different type of problem, and actually one very big difference between the two problems is that there's more geometry in percolation, right? In a graph, you just have nodes and edges. There's not really distance relations between them. In percolation, you have a grid. You have localized regions. You also have the shape of the grid. You don't have to do a square grid. You could do a hexagonal lattice, say. So it was first proved in, I believe, the 60s by Keston that there is a threshold phenomenon here as well. And by that point, percolation had really connected to the mathematics community. It was studied by physicists, but also by mathematicians and statisticians. So then what did the random graph world offer for percolation? Well, I think it told us something very interesting. Okay, so how does percolation model a phase transition? What's called P temperature. So as the temperature varies, right, we're going to get more bonds as the temperature goes higher. Things are more likely to be interacting with each other. That is how I believe physics works, not my expertise. And you get these very sudden changes in temperature from liquid to solid. And at the temperature of transition, we have what's called critical percolation. So on the left here, I have subcritical. I get components that are relatively small. On the right, I get large components. Or sorry, in the middle, I guess on the right, I get like almost everything in one component, which you can, I think, analogize with solids, right? So on the left, you have a bunch of different pieces floating around like a liquid. On the right, you have a rigid structure, and maybe there's a bit of fluidity available inside of it, but they're constrained. And then at this critical percolation, this sort of would tell us what it's like for a liquid to form a solid. How does that process emerge? And that's an interesting and valuable thing to study from a physics perspective. And it's exactly analogous to the evolution of component sizes in GNP. It turns out the scaling behavior at criticality is the same. This was established about a decade after Bullabach. And it's sort of a universal property of the independent of the specific instance of percolation that you're talking about. So the way these transitions occur shouldn't depend on the type of matter that we're dealing with, on the way it arranges itself. It just depends on sort of how likely bonds are to form. I believe physicists conjectured this. It's a little unclear to me, but it's not clear to me that physicists believe this specific property of percolation was universal before the random graph people figured it out. So this is where I was saying earlier, you have this phenomenon where you start with a toy model, and then you go to a real model. So the random graph is a toy model. The grid is a real model, but really, I mean, that's a toy model too. And then you have the real world. And the hope is that information travels along these settings. And the random graph is sort of the simplest setting where this phenomenon occurs. And so by understanding it in sort of its simplest setting, it's sort of easier to get a handle on what might occur. And then you have to check, does this intuition that I'm developing translate to these other settings where it's less obvious? So this is just a very standard process of how knowledge is constructed, I think. But what's interesting to me about it is right here, like Erdos never worked on percolation. Bolobash actually did quite a bit. Many of his other proteges did as well. But Erdos never made that leap. And yet he still created this body of knowledge that transferred directly. It asked the right questions. It introduced critical techniques for the method, and it actually like provided practitioners to solve the problems in the new setting, in the new but perhaps classical setting. So I think that this is like a very concrete example of what Cody was talking about, that these peripheral communities are sort of off doing their own thing, and they stumble on something that works. They tap into the broad community, and suddenly some of them become central. But more importantly, they've added something new. Okay. So I think that this is, when I think about how mathematics is applied, and I'm the wrong person to ask. I don't apply mathematics in my own life. I don't have like a philosophical or sociological framework of how to think about this. But I sort of view there as being like three pillars of Goldilocks mathematics. Goldilocks in the sense of Alan's talk. Mathematics will codify ideas. It offers a new language to make precise statements. It brings a different sense of what is possible for questions to be asked. It provides, I mean, giving precise definitions is so important, I think, in many fields. I remember there's actually a program where mathematicians are brought into the military to work as consultants. And I heard about someone in this program, they'd spent a year coming up with a bunch of, I guess maybe half a year coming up with a bunch of thoughts about like how they could have some positive impact on the military. They're giving a presentation to a bunch of generals. And the first slide is like defining a very like basic term, something like strategy. So they offer a definition, and then the entire rest of the talk was just the generals debating whether this was a good definition, how it was a good definition, and what they learned from the definition itself. They never made it to any of the content. This is a very valuable service when it functions effectively. A second piece is a toolkit, right? They're bringing new methods to bear on old problems. Not just new language, new statements, new questions, but new methods. And then there's this talent pipeline. And I think you see this in so many settings. It's not just mathematicians that are talented, but it's so common to see people from, I guess, areas with high levels of abstraction parachute in to areas with lower levels of abstraction and offer something meaningful without necessarily showing up with much domain expertise. I mean, I don't know if you need to hear examples. Like the first author on the first sequencing of the human genome came from my community of mathematics. After grad school, he sort of switched gears and suddenly he's a geneticist. It's not uncommon, but especially when a connection like this is formed, then you'll get, I think, even stronger practitioners appearing, people who are sort of already showing up with a unique perspective and toolkit. So percolation is a winning example of these pillars. There are multiple Nobel Prizes in percolation and also multiple Fields Medals, which is kind of the most prominent prize in mathematics. Of those Fields medalists, I would say one of them is in arguably the Erdos school. Okay, does anyone have any questions about this sort of, I guess you could call it a mechanism of how mathematics applies in this peripheral way?
I guess something I was kind of wondering about is, there's kind of surprising versus non-surprising connections. I think
Yes.
Monstrous Moonshine was a very surprising connection. And so I'm just kind of wondering how much, I mean, this is kind of more of, I guess, a philosophical or general question, but how much of this, especially with random graphs, was there like something really unexpected, or was it a lot of the applications of random graphs, like, oh, okay, it makes sense, it's in line of what we were thinking. So I'm just kind of curious of if you have any thoughts on
Yeah.
that.
That's a great question. I think that, I guess what I'll say is that I think that I think the connection to percolation, right, on the face of it, it makes a ton of sense. I think the fact that phenomena were discovered in the random graph setting that translated to the physical setting was pretty surprising at the time and very exciting. Um, so that there would be a relationship at all is not surprising, but how it arises is. I think for like things like randomized algorithms, um, it's almost like you couldn't even study them in a really sensible way until you had this mathematical methodology. Um, and so this is sort of one of these things where, like, the codification really stepped in, is maybe a way of phrasing it. So I don't know if there's anything where it was like so shocking. Um, I think there's also another element though, which is where we're headed next, which is that having the toolkit sort of in the water, so to speak, um, is also really, really valuable. Okay, before I get into that though, I want to talk a little bit about this sort of too hot and too cold story from right. There's such a thing as too much or too little math. Um, and most of these, I think these examples are on the too much math side of thing, which is that mathematicians often engage in pedantry. They demand an unreasonable level of rigor. They get upset when something seems to work, like neural networks, but they don't have a good justification for it. They'll say that's not science, that's engineering. Uh, then there can be a methodological mismatch, which can also lead a sort of misdirection of resources. So when the tools dictate the questions, you lose the original objective. So it's very common that a mathematician will hear about a problem that's useful and important, say, oh, like that's not so interesting to me, but this facet of it, which doesn't have any practical applications, is really cool. And so I'm going to study that. And if they direct the field and the field's resources in that direction, mathematically that's interesting, but it's a loss, both in the methodology and also in just the resources of talent, of time, of money. So this doesn't always pan out perfectly. And I think the next scenario I want to address is more confusing to me about how to think about it. And that's actually the methods that Cody was using, that others have used, network science. So what is network science? I guess in a technical sense, a network is a graph plus some sort of measurement of significance across edges. Some sort of weighting. That's, I think, the formal definition you'll read in a book. But really, what is network science? It's applied graph theory. Whether that's in sociology, in physics, in chemistry, in biology, there's sort of this umbrella network science, which I think of as applied graph theory. And why did this become such a thing? Well, in the 90s, a small graph became large. And that's not to say that the internet is the only place where network science proved useful, but I think it's the value generated in understanding the internet is so profound that it demanded resources. And this was clear pretty early on, right? I mean, what is Google? Google is a graph algorithm. That's what PageRank is. It's an algorithm on graphs. It is worth hundreds of billions of dollars in economic value, like market value, and it's worth more probably in like real human value generated. That's a small piece of this. Well, maybe not small, but it's small from the perspective of how many examples there are, not necessarily their relative importance. Okay. So a new source of questions showed up, and you had to understand it differently. And so there's two features here that were new to graph theorists, arguably. So it's small worlds and it's scale free. So what does small worlds mean? It means that typical clusters are small, but things are still closely connected. So the term 6 degrees of separation is a popular description of the small world type phenomena. What does scale free mean? It means degree, the number of things that a given node is connected to, follows a power law. So all scales are represented. So this is a different graph of the internet from the one we saw in the previous talk. But again, right, you see that there are these clusters, which are in the same color, and the clusters connect to each other very densely within each cluster, and they connect to each other sparsely outside of their clusters. And so what that means is if you're in a large cluster, you have many connections. If you're in a small cluster, you have few connections, and then the clusters themselves demonstrate the same type of behavior. So within a cluster, there will be clusters and so on. So this is what they mean by scale-free. And so it was observed throughout, well, I mean, the small worlds phenomena was first documented in a paper by Milgram in 1967, a psychology experiment, actually. The scale-free phenomena, I can't give you a good history in the way that, say, Yuchi could give us a good history of neural networks, except to say that the first explicit connection to the internet was made in, I think, 1998, that this sort of scale-free type phenomena existed. And it was in 99 that a model was introduced that satisfied all these properties, these two new properties. So the Erdos-Renyi random graph does not. Instead, we have something called preferential attachment. So you add one vertex at a time, and when you add the new vertex, you connect it to some fixed number of other vertices, and you're more likely to connect to the ones that have many neighbors already. So this was introduced, it's in a paper by Albert and Barabashi. I have them flopped in the photo. So that's Barabashi on the left, Albert on the right. Barabashi was the last author of that paper that formed the field of the science of science. And they sort of introduced this, and it's supposed to model genetic, neuron, social, and internet networks. Right? We want this small world phenomenon. We want this scale-free phenomenon, and they gave reasons to believe, empirical and heuristic, that this model should work for that. So this model was also introduced by Price in 1977, specifically to understand citations of academic papers. It was published in a bibliometrics journal. So, right, the idea is when you cite a new paper, you're more likely to cite a paper that's been cited a lot than one that hasn't. It makes sense, either from a popularity model or from a usefulness model, or both. You can be agnostic as to why, but clearly that's a behavior that occurs. And in fact, it was also introduced in 1925 by Ewell to count species within a given order, right? So why are there so damn many beetles versus other orders? And again, it's sort of a speciation model, right? When I add a new vertex, well, it's split off from some other species. Which order is it going to go in? The same order. So if you have a model where species don't go extinct, but they do form, then it's essentially this model. And I think this shows again that a huge part of significance, right, is about answering questions that matter to people and forming communities around those questions. Ewell did not, and it's not like his work was never mentioned or cited again. But there wasn't a critical community around understanding this type of mathematical biology. There wasn't a critical community about understanding citation counts. And the internet, I think, is the sort of catalyst for why wanting this different model of graphs became so critical. I think it's worth commenting. Barabashi and Albert, in their paper, they're really talking about this in contrast to the Erdos-Renyi random graph. They're aware of it. It's in the air. Barabashi did his master's in Hungary. I was talking with one of my Hungarian colleagues about who's a contemporary of his, whether he knew him. Turns out no. Whether he could say with confidence that Barabashi learned about random graphs in grad school. Yes, pretty confident. Right, I think it's not an accident that he is Hungarian. This was in the air, this was known, and he was one of the people connected to this peripheral community, or he and his advisor, perhaps. Okay, so this, I think, maybe also gives us a reason, at least, right, one of the takeaways in Yuchi's talk was about how there's going to be multiple discoveries and the last discovery is generally the one that gets the credit. But I think there's good reason for that, right? Which is that the last discovery is the time when the idea really had a sociological function. Okay, so whence Erdos in all of this? Well, my main takeaway, right, is that for applications, math is always a community on the periphery. And it renders immense great value, and it extracts little. So partly this is me telling you if you're ever in a position of authority, you should fund math research. I would appreciate it, but I think that it would also be of broad utility. Okay, so here's an example of a result. So this is Bolibosh, also Borges, Chase, and Reardon. These are all people I would place at least partially or fully in the Erdos school. And so, like I said, the Albert Barabashi paper gives heuristic reasons why preferential attachment should satisfy the power law. Bolibosh, Borges, Chase, and Reardon proved that it does with explicit exponent. In fact, I think this is also in Ewell's paper, as well as proved again by Simon, Herbert Simon, who was mentioned in the previous talk in the 1950s with more general methods. So that this was discovered by them, I mean, in some sense, it was partly known. I think they do have a more general result significantly. It was heuristically believed, and for a physicist, often that's good enough. I do think it's a question like, what is this result good for? It's been cited 1,000+ times, according to Google Scholar. It's not clear to me that this answers network theory questions. This might be too much math. The flip side is that many mathematicians, sorry, I need to look at some notes. There. Okay. So I think it's unambiguous that many of the key methods that are used nowadays to study networks were developed by mathematicians, including recently after the advent of network theory as a theory of science as opposed to a theory of math. And understanding these sorts of phase transitions mathematically, I mean, even in the network theory context, the Erdos-Renyi graph is valuable. If you want to understand how connected a network has to be resilient to targeted attacks, Erdos-Renyi provides you a useful model for that. But I think at this point, it really becomes the value is less about the specific example of the Erdos-Renyi random graph and more about the community that formed around Erdos. So several of his proteges, I think most notably Laszlo Lovász, Fan Chung, and Noga Alone. These are very prominent mathematicians who've done, I would say, genuinely useful work for network theory from a descriptive sense, from a theoretical sense, from, I guess, like, in basically every sense. I'm not saying they're the only practitioners who've done useful things. I'm not saying mathematicians are the sole community contributing, but it's very clear that they are. I just think it's less clear cut which particular facets are valuable than it was with percolation. So I'm not really sure I have a conclusion here, except to say, I think the community element is what drives the meaning here, the impact here for me. So maybe I'll have better thoughts about this in the near future, but for now, I think I have to wrap it up there. So thank you. for listening. And I hope that you enjoyed and followed along, and that this example becomes a useful uh, bit of for developing your own intuition about how this sort of knowledge is formed.
Yeah, thank you very much, Zach. Really enjoyed your talk.
Okay. And I guess there's time for questions.
Yeah. Does anyone want to ask any questions?
I have a question.
Yeah.
Yeah,
First of
go
all,
ahead.
thank you for a very interesting talk.
Mhm.
I have a question about uh Fan Chang's work, the spectral graph theory,
Yeah.
and something that came to mind is opinion dynamics models, where um basically like ideas are seen as the diffusive process and modeled with like spectral graph theory. And
Mhm.
I was wondering if there is any connection to to random graph theory mathematically and to properties of and co-communities form, like because it might be difficult to kind of say in a binary sense
So wait,
of
so
connection.
I'm sorry, I think I missed, you said that so spectral graph theory is being applied to what sort of models?
Oh, opinion dynamics.
Opinion dynamics.
Yeah.
Okay. And so I guess, right, I mean, in some sense, right, the framework of how you study a sort of organically occurring graph is you kind of imagine a process that generates it. This induces some distribution on graphs, and you would like to understand what features are sort of consistent across that distribution, right? So this is, I mean, in that sense, literally, like any type of inference on networks is going to be, or even like understanding qualitative properties of real world networks is going to have some random component of analysis. I'm not familiar enough with the specific models or the specific instances that you're talking about to say whether the Erdos-Renyi graph in particular is relevant. I think I would need to be familiar with both the graphs and how spectral graph theory is being applied. Um, I guess maybe one thing I can say is uh, if Tracy Whittem distributions are showing up, then it probably is connected to Erdos-Renyi random graphs.
Thank you.
Yeah.
All right, yeah, if there aren't any more questions, we'll wrap up here. Again, thank you for your time, Zach.
Oh no, my pleasure. And yeah, thanks for everybody for sticking around. I know it's a long day and it was a good one.